Okay, welcome back everyone to The Process, which is my 7-part series on deep diving into how Elixir processes work. So before we get started, there's a couple of changes that I want to address. The first one is that I've renamed Chapter 3 to The Trouble of Concurrency, Task to the Rescue. The reason why I did that is if you look at the old title, it kind of makes it sound like tasks are a problem, and in fact, exactly the opposite is true. Tasks are awesome, and they fix some problems that you might run into as a result of concurrency. The second difference is that I've shaved, and I did that in part to kind of highlight the difference between this process basics, which is kind of like super caveman Erlang VM stuff. It's really low level and raw, and you shouldn't be using any of the things that I showed you directly in the way that I showed them to you in the last video. You should use kind of a more modern, cleaned up interface to all of these basics in the form of task and GenServer and supervisor and registry. These are things that Elixir gives you. It presents a very well-tested and well battle-tested interface to handle a lot of the weird corner cases that you're going to get as a result of concurrency. But all of those things build up on top of those basics that I showed you before. So just to reiterate, don't use spawn, don't use receive directly unless you really know what you're doing. Instead, use all of these abstractions that are provided to you by Erlang and Elixir. Okay, so first I'm going to go over a couple of straggler content bits that I forgot to go over in the last video. So let's get started. I'm going to start up a terminal, and let's go into the Elixir shell. And one of the things that I forgot to show you was putting everything together. So spawning a function as a process and then returning a result back to the calling process. And I think it's a good thing that I'm going to actually put all this together in this video, because we're going to see how this can go wrong and why you shouldn't be doing things in this way a little bit later. So it'll be nice to see this twice. All right, so here's the basic code, and I'm going to run all of it real fast, and then we'll watch it do its thing, and then I'll go break it down line by line. So we're going to wait. It's going to print out hello, and then we're going to get the result of the call, which is 47. So how does this work? So first I'm going to take the self, which is the console process, bind it to the variable console. That's going to be closed inside of this lambda. This lambda is going to sleep for 5 seconds. Then it's going to print hello. And then it's going to send its response back to the console, which would be 47. And then I'm going to block the console on this receive, and then spit the result. The 47 will come in, and it'll spit that out as a result. And then the result of this expression is going to be 47. And so that's what happened there. I do also want to note real quick that if I do that, let the spawn function go, we're going to see hello in a few seconds. There it is. And then I do receive. It still works because that 47 was sitting in my mailbox. This receive is basically asynchronous. It can happen much later. It can happen before the result comes back in. It doesn't matter. I'll get the same result. Okay. Second thing that I kind of wanted to do that I forgot to do was to show you that this can work in the opposite direction. So first of all, we know that the console is a process and it has a message queue. But what I really forgot to do was to show you that indeed this thing that we're spawning also has a message queue, and it's independent, and it can do things, it can do things as you would expect, right? So what I'm going to do is I'm going to spawn a function, and all it's going to do is it's going to block. So here we go. That's what that looks like. It's going to launch a function. That function goes into a receive block. It's going to wait for a message. And as soon as that message comes, it's going to inspect it, and then the function is going to end. Okay, so let's go ahead and do that. And so process.alive So is that PID 138 alive? Yes, it is. It's just blocking on a message, but it still exists as an entity in the VM. It's just kind of hanging around, waiting for something to happen. Now, let me send that process a message. And that would be V8. And so what happened was I sent that message foo, it received it, and then it inspected it. That sent it out to the console. And then the result of send is the term itself, which is how we wound up with that. Okay, now if I run process.alive, and we're going to do V8, it's false because this receive block has cleared. The function no longer has any more instructions to run, and then it finishes itself up. So those were the kind of the two topics that I forgot to cover in the last video. I'm terribly sorry, but I think it'll be nice because that'll kind of lead into this next video. Okay, so part two. So part two is about tasks, which are basically an Elixir abstraction that doesn't, as far as I know, exist in the standard library of Erlang. And it's a set of conveniences that makes doing all of this asynchronous work a lot saner, and it covers a lot of sort of the corner cases that you would miss. Now, traditionally in Erlang, you would use GenServer to do these sorts of things, but I think it's reasonable to say that GenServer is kind of the wrong abstraction to do something that just has a linear control flow. And I think this is kind of one of the brilliant and maybe underappreciated things that Elixir brings to the table over Erlang, is this very simple sort of asynchronous, concurrent, but one track subject of execution, and that's what the task is. So the first thing I want to say is that task is just like spawn. And then I have in the parentheses here, but use task. And I'm really serious when I say use task. So let's go ahead and do this. I've got some code here I'm going to paste in, and we'll take a look at it before executing it. This is going to be basically analogous to the spawn function that we did before, and also it's going to be analogous to this spawn function here. And so what I'm going to do is I'm going to sleep for 5 seconds, print hi there, and then the function itself will return 47. All right, so let's see what happens. So we get back an OK PID tuple, and then it says hi there, and then the 47 is gone. Just like how spawn erased that 47, went into the ether, went to dev null. Same thing happens with task. So you can't, out of the box, expect to get a result out of task. And then we're going to play around a little bit with that later. So one major difference is that unlike spawn, task returns this OK tuple. And that's very important. The reason why it's good that task makes your life a little bit more complicated when you try to destructure it is because this is the form that supervisors expect for other things like GenServers. So supervisor expects an OK tuple or an error message or an error tuple responding to the launching of a process. And because task returns an OK tuple, that makes it directly compatible with supervisors. And we're going to go over that more in chapter 4, supervisors, right? But for now we'll just leave it at that. That shape is very important. Okay, second thing that task does is much more subtle. I think a lot of people who use Elixir on a daily basis don't know about one of the more special things that task does, and it's a little bit more complicated to explain in this session. But guess what? It's going to be incredibly important for chapter 3, the trouble with concurrency, task to the rescue. So, look, I'm going to do a shameless plug for the next 2 episodes right here. If you want to learn more about how this shape was important for supervisors and how tasks really are like mind-blowingly amazing and really fix one of the major problems with concurrency, check in to this channel, and you can do that by subscribing, and you'll be notified when I complete chapter 3 and chapter 4 of this series. Okay. So since I strongly recommend that you use tasks over spawn for these 2 reasons, and we'll uncover one more reason a little bit later in this episode, I thought it would also be a good idea to show you my preferred way of writing task modules. And if one of the earlier videos I made was something called the router pattern, which shows you a sort of best practices way. I mean, it's not commonly accepted, it's the way that I do it, but what I feel is a best practices way of organizing your code in around a GenServer so that it makes your code easier to read, and it makes a lot of the shortcomings of how GenServers are architected much more easy to parse. And so accordingly, and I'll put a link to that video in the video information, but I have a similar way of organizing tasks, and since tasks are much simpler, you can imagine that that this is a lot simpler than the router method, which is what I talk about in the GenServer episode. Okay, so let's take a look at this. So I typically define an API right here, and then immediately below a set of implementations for each of the functions that belong in this module. So in this case, I'm just going to have one task. It's going to be called heavy lifting. And it's just going to be a pretend heavy lifting thing. So I'm going to go do something that's going to take a while, come back. The answer is going to come back later. I want it to run asynchronously. And so here it is. I'm just going to task.start. I'm going to throw away the OKPID. I mean, normally I would probably return the OKPID, but just for this, I want to show you, I just want to return an OK. And then I punt to a private function called do heavy lifting. I always have tasks. So in the GenServer video, you saw that I had my router implementations with _impl at the end. I usually do underscore for the code that runs asynchronously, and it should have the same name as the implementation call. And finally, whether or not it's defp or def is up to you. If I plan on doing testing on the contents of this and I don't want it to spawn a new task, I will make it def. And if I don't plan on doing any testing, I'll just make it be defp. And there are some cases where you do and some cases where you don't want to do testing on these. In this case, it's such a simple function that if I were to write xunit tests, which is a topic that I'll go over in the next episode, I will typically make this such a simple task just be defp. Okay, so looking at this function, basically it's going to do the same thing. It's going to process.sleep for 5 seconds, and then it's going to print heavy lifted, and then show the argument, and then return the value 47, which is going to get thrown away. But note that I've closed around the argument here. So I passed the argument here into the heavy lifting function, and the lambda for the spawn, or the task.start, which is equivalent to spawning, closes around the argument that it gets passed in the heavy lifting function. All right, so let's just run this real quick. And of course, I'm going to pass foo. Let me make this a little bit bigger so you guys can see more information. And so, of course, it will wait for 5 seconds. And then you see heavy lifted foo, and then it's done. Let's take a little bit more of a peek at this. So I'm going to do OKPID, or actually, OKPID. And I'm just going to return the PID out of this. recompile. And then so I'm going to do playground.heavylifting, and then I'm going to do process.alive. Oh, we'll have to try that again. It's alive, and then once it finishes, it is, of course, no longer alive. All right, great. So the next thing that I want to introduce you to is the idea of start link. So this is kind of an important question. And what a link is the Erlang VM's way of allowing you to define failure domains. And one of the things that sometimes I say is that Erlang and Elixir are failure domain driven languages. So what that means is that the virtual machine is extremely has lots of is extremely like instrumented with different ways for you to define failure domains. And what that means is that if you have a certain set of actions that are happening in concert, if one of them goes horribly wrong, it should have a blast radius. The default blast radius is a blast radius of 1, which means the only thing that fails when you fail is the process that's running, right? And this is kind of what people usually say when Erlang and Elixir is a let it crash language, right? So if something bad happens, just blow that thing up, have it panic, have it fail, whatever you want to call it, but everything else in the virtual machine is completely untouched. This is kind of a pattern that other programming languages have discovered recently via Kubernetes, right? So, you have a problem in one of your OS processes and it blows up, you panic, Kubernetes restarts it. Well, Erlang and Elixir let you also be a little bit more sophisticated than just a blast radius of 1. Sometimes you have asynchronous processes that are occurring, right? And maybe you want them to be tied to each other because they're intimately related. So if one of them goes down, you want everything else related to it to also go down. And just it's the sort of the Toyota pull the brakes on the assembly line if something wrong happens. You want to limit the blast radius outside of everything, but also you have these other things that are codependent that you want to extend your blast radius to, right? And so that's what linking allows you to do as a sort of a first order approximation. We'll go into more detail later in the supervisors chapter. Okay, so what happens if I start link? So what is the difference here? So let's recompile. And then I'm going to do start heavy lifting. Okay, so we're going to wait 5 seconds and then heavy lifted. Nothing. No difference. Okay, then why did we do this? Remember, start link is about helping you define your failure domain. So what has happened is that the console's failure domain has been merged with this task's failure domain via the start link. Okay? And so in order to really see the difference, what we need to do is we need to actually cause a failure. So I'm going to raise here. All right, now let's recompile it and then run it. Boom. A few things you should notice. First of all, the number next to the IEX has changed. It's gone from 11 to 1. And that should be immediately a red flag as to something interesting happened. And it says also, like, let's read this error. Task PID 216, that's what I launched, right? Started from PID 0155. That's the console PID. I don't know if we ever exposed that before, but that was the console PID. And then it says, okay, here's the runtime error that got triggered. And then exit from PID 0155.0. So that means the console itself exited, and then the number on the IEX got restarted because we started an entirely new shell, as you can tell, because it says, hey, interactive Elixir, press Control-C to exit. So we basically wound up restarting the console. And that's exactly what you would expect if you did a start link, right? Because now these two processes are linked. The task process raised, and it caused the console process to crash. So let's just double check that that's the case, right? So first I'm going to do self, and then we're going to note that the PID of the console is 218.0. And then I'm going to run this playground.heavylifting. We're going to get a crash. And if I do self, I've got a new PID number for the console. And of course, the error messages here say PID 218 and PID 218. So that's fundamentally what happens with a start link. Now let's go back and double check to make sure that this is a real thing. So what happens if I do start instead of start link, right? And I'm going to run this function. There was a runtime error, but my IEX numbers didn't change or incremented in the normal way. So we do see that task PID 241 started from PID 222 terminated, but PID 222 is still the PID of the running process. So that's kind of the difference between start and start link. Start link means merge the failure domains of these two processes, and start means run it, but in its own detached failure domain. I think this is like a really, really important distinction to make about how this is one of the things that really makes the Erlang virtual machine special. So let's go back to start link for a second, and I want to do something a little bit different from what I did before. So let's recompile. And I want to demonstrate that this linkage is two-way. So not only can the task crash the console, but the console, if we cause the console to crash, it can cause the task to crash. And so how I'm going to do that is I'm going to execute this before, and remember, I need to delete this raising here. So let's recompile. So I'm going to run it as I did before, and this time I'm going to crash the console. And then when I crash the console, you'll see that nothing that nothing will happen, and that the PID of the task will have died. So let's go ahead and do that. So I'm going to run that, and then I'm going to kill self, and you can see that I ended that 222 process, which was the console, and now the console has a new IEX number, or has rolled its IEX number back to 1, and I see this interactive Elixir, which suggests to me that the console has given up the ghost. Let's double check with self, and you can see that the process ID indeed is a new process ID from the previous one. But the other thing is that let's see if we can't recover. So you notice that we never got the expected response, which is heavy lifted arg, right? So let's just see if we can't try and get that. So process, let's do, so there's a special function called PID, which only works in the console, so don't try this anywhere else, but I can define the PID from a set of values. So we're going to try and get at this the PID that was the task that I launched from the heavy lifting function. So that's what that looks like. And then process.alive. And so that PID 0277 is indeed not alive. Now let's do it this way. So I'm going to delete link off of the end of this task, .start. And then I'm going to get ready to kill the console. And then let's run it this time. So now the console and the task should be in separate failure domains. So you can see that the shell got killed, and still afterwards I got the heavy lifted foo, so which means that the task was still running, even though the console itself wound up getting crashed. So hopefully that kind of sheds some light onto this idea that Elixir and Erlang are fundamentally about making it easy for you to not only do concurrency, but define failure domains for your concurrently running processes. And I think this is really unique still to basically Erlang and Kubernetes. If you can't do this so easily in Go, for example, or Rust without really drawing upon either libraries that other people have written, and I still have reservations about whether or not the robustness of what you would be trying to do in other programming systems would be quite as good as it is with Erlang. Remember, this sort of practice and the code behind the VM have been battle tested for 25 plus years. People have been doing concurrent systems in Erlang for a very, very long time. Okay, so the other thing that I want to do is I want to show you how we can sort of take this failure domain idea and really construct a series of stitched together failure domains, right? So they're going to be transitive. So process A is in the same failure domain as process B, and process B is in the same failure domain as process C. And because of that, if process A dies, then process B dies, and then if process B dies, then process C dies. So let's substitute in some code here. And so let's kind of go over what's going to happen here. So I'm gonna detach this main task, the do heavy lifting task, in a task.start. So keep in mind that this is going to be in a different failure domain from the console. And what is going to happen is I'm going to launch two subtasks. Now, normally, if I were being more disciplined, I would probably put these subtasks in their own functions to be run in the same fashion as with this sort of an organization where I define the API and then write implementation functions. But I'm not going to do that for the sake of brevity. And then, and so what's going to happen is that two different processes are going to happen. Let's just pretend that I've got two heavy loaded tasks, one where it starts downloading the whole internet, and then one where it reports that it has started downloading the whole internet. Now, keep in mind that this is going to launch first. It's going to take a long time, 5,000 seconds, and then it's going to print its result, and then it's going to send the heavy lifting task the message done. And when it sends that done message, it's going to print out, I'm done with the task. Great. And then there's going to be a second task where it says, I've reported that I've started downloading the entire internet. Okay, ready? So let's recompile this and let's run it. Oops. So first it reports that it has started downloading the internet, and then 5 seconds later it has downloaded the whole internet, and then it's completed with the task foo. I'm going to run it again, and we're going to take a look at process dot yes, it's still alive. Once it has downloaded the whole internet, it releases this receive block, and then the process has died, right? So that process is not alive. Okay, so now what I'm going to do is I'm going to inject an error. then we're going to try and run this. And what's going to happen? We're going to get that runtime error oops in the outside process, and that should have killed 347. And note, we're going to wait a little bit while. We're not going to see downloaded the whole internet trigger. We're not going to see this print, of course, and we're also not going to see this. And let's just verify that this PID 347 is gone. And V7 is false, so it's not alive. So what exactly happened here? When this task died, because it raised, it crashed the parent task, which is this heavy lifting task. And after the heavy lifting task died, it killed this downloaded the whole internet task, and the whole set of 3 processes came down together as a single failure domain. And this sort of a technique for managing failure domains is a very important part of more advanced Elixir and Erlang engineering. The ability to do this is part of, in like so very few lines of code. I mean, I didn't have to all I had to do was call it with start link instead of start, right? And this is part of the standard library, the ability for you to control blast radii of different things that are flying around in your virtual machine is very, very important. Okay, the last thing that I want to do is to revisit the idea of returning values from a task. And so remember, before we returned a value from a spawn by sending back the message to the caller. So what I'm going to do is I'm going to copy paste in some code that basically does this, and we're going to run through exactly how that works. Oops. And so we're going to use the same heavy lifting framework, right? And it's going to stash the return address, which is self. Now, be careful. It's important to note that this heavy lifting function is called by, in this case, the console. It's called by its caller, and everything here in this function, except for the stuff in this lambda, runs in the context of the process that called it. And then when I jump in to do heavy lifting, this happens inside of the context of the newly created process. So self here binds to the console self. And if I were to call self in here, it would be a different value. I then close around the return address value, right? And then I run the code, and then I send back the return address, the result of the function call. So let's go ahead and run this. I'm going to start a new shell so that we can start from scratch. And let's go ahead and run this. So we're going to do playground lifting, and then we'll call it with foo. And what we expect to see is we're expect to wait for 5 minutes. We're gonna io.puts heavy lifted, and then we're gonna send the parent process the message done with argument. It's going to receive it, and then it'll unblock it, and then this function will have completed. So you're going to notice that I'm going to lose console control as soon as I execute this function, because it's waiting on this receive. So 5 seconds. Heavy lifted foo, and then I got my result back of the function call, which was done with foo. Perfect. Now, do you see the problem with this code and why this code is generally not a good solution for this problem? Well, if you're paying attention during the previous cast, you might have remembered exactly how the mechanics of this receive works, right? So what if I were to do something like this? So I'm going to preload into my message queue the troll face atom. And then if I run playground.heavylifting foo, the return result is going to be troll face, because it asynchronously launches this function and then it immediately goes into this receive block. Now, if I didn't have anything, if I was starting from a fresh mailbox, then yeah, it would give me the result that I expected. But if there's something else in my mailbox, I might not get the result that I expect. And this, I think, is what is super important. In the previous video, how I was saying that Erlang and Elixir give you a way to define API contracts around your modules, but there is no clear way to give an API contract around your what occurs with message passing between processes. This is what I'm talking about. And to some degree, the constructs of GenServer and as we'll see, Task give you a set of really good practices around how to make sure that this sort of a thing doesn't happen. But here's the thing: like you might say, oh, I'll just never get a message that I don't expect. But maybe your process has subscribed to some sort of pub sub, and you have zero control over what that pub sub is sending you. Or maybe you're subscribing to notifications that a process has died or a node has gone down, or some other VM level thing, and you just have limited visibility as to the defined surface area of messages that you can get. So let's talk about sort of the basic way that you would go ahead and fix this. Now, one smart thing that you might want to think about doing is tagging this as some sort of tuple. So like heavy lifting return address, and then we'll match on heavy lifting result. And so, that's nice, because if we do something like this, let's recompile and then show that it works. So process dot send, or let's send self troll face, and then I can do playground.heavylifting foo, and troll face will not match this shape, right? So that's why you can see it's blocked. And I don't know why this didn't work. Oh, right. Sorry. This doesn't belong here. This belongs here. So I'm going to send a tagged value back. Oops. And we got trapped inside of the receive block. Okay, so let's preload a troll face, and then playground.heavylifting foo, and then what we'll see is that we'll wait 5 seconds, and then it will send this tagged sort of structured data, and then even though I had that troll face in there, it gave me the correct return value, right? And so let's flush, and then we'll see that the troll face message just was there, but it was completely ignored because it didn't match the correct shape. So this is one way of defining a good API for any process, this sort of process exchange here. But it's not really perfect. So one of sort of the corner conditions is what happens if I started a task that emits this sort of HL response, but it was kind of maybe like a network call, and so the internet can be unreliable. Fiber optic cables get cut by careless construction workers, for example, and so maybe I put in some sort of after 5,000 seconds just give up, right? And then I do another call, and for some reason that message from the previous run was delayed instead of canceled. Then I can potentially get an intercepting response that will mess things up, because it will still have this correct shape. Or perhaps maybe somebody malicious could decide, a malicious or over chatty process inside of my system could be sending these HL shaped messages for some reason, and I have no control over that. So what I really want to do is I want to have a defined way of really tagging this call and saying, hey, like this is the subject matter. So, you know, a good email has a return address and a regarding line, right? A line that tells you what this message is regarding. So what we kind of want to do is we want to construct, that's what we want to construct, right? All right, so let's go ahead and construct that. And so first thing I want to show you is a function called makeRef. So one of the intrinsic data types inside of the Beam virtual machine is something called a reference. And that's what that looks like. It's just a really long integer, basically. But what references are supposed to be are a marker to a time and a place. And by place, I really mean a node. So if I've got a virtual machine running here, and I've got a virtual machine running in a cloud, and a virtual machine running, you know, on the other side of my local network, all of these virtual machines can generate reference tokens, and they're guaranteed to not collide, at least within some absurd multiple of the lifetime of the universe or something like that. And you know, you could get unlucky, really, really, really unlucky, but it's basically not going to happen. And so that's what these reference tokens are. They are unique markers for time and place. So how do we use these to make sure that our messages are what we expect? Okay, so the way we do that is we do a return ref, and then we're going to pass this return ref in as well. You might want to package this as a tuple instead. And we're going to package this in within our response, and also drop in the return match against the return ref in our receive block. Okay, so let's show that in practice. So we're going to wait 5 seconds. It's going to have completed its thing, and it's going to respond with the correct answer. And here's the kicker. If I try to do something like this, send self. So let's add a token into our message queue that has the same shape. And then try to short circuit this receive block. And you notice that it didn't fall through immediately, and it gave the correct response instead of giving troll face. And if we flush our message queue, that troll face message was basically ignored because the reference didn't match with the reference that I generated on spawning the task. So that is how you make sure that there's coordination between the task that you run and the return response that you expect. Okay, that's a whole ton of boilerplate. You don't really want to be running that every time you run an asynchronous process that needs to return some sort of result. Well, the good news for you is that the Elixir folks have packaged something like this already inside of the standard library, and it also does one extra thing which I haven't even talked about yet. So let's just show you what that looks like. This is what it looks like. So I'm gonna go ahead and assign. Well, let's just go ahead and run this. So it's the task.async function. The task.async function takes a function it takes a zero arity lambda as its argument, and then it will run that stuff asynchronously. So let's take a look. And we got back some sort of a result, and then we got hi mom, and then that 47 is still kind of currently AWOL, but how do we receive it? We get it by doing this task.await that previous value, and then we got the 47. So this is what in other languages you might call a future. It's a token that says I expect a result to come back here in the future. And as you can see, it's got 3 pieces of key information: the PID of the thing that got launched, the PID of the running process, and also a reference which says this is what I'm talking about. So this is effectively our return address here and our reference. So I'm gonna do one more thing, and then what we're gonna do is we're going to rerun this function, and then we're gonna kind of spy in on the message mailbox. And we're gonna know it's done because it's hi mom, and so it should have sent the message back in. And then let's take a look and see what's inside. 2 things are inside here. First is exactly the same type of construct that we used before in our experiment up here, right? It's got this reference and then the payload. Here we got the reference and the payload. And we also have this other message here. This is down, reference, blah, 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 process, PID, and then normal. What this is this is just the Erlang virtual machine sending out a message saying that, hey, like this task has finished. Now, I will say that like one of the things that it does is that one of the things that running task.async does is it subscribes to a notification that says, hey, when this PID dies, just let me know. So the reason why it does that is let's say you decide to put in like a really long await. So I'm gonna wait for 10 minutes for this result to come back because it might take a long time. You don't want to be left hanging if the process has died real fast. And so by being able to subscribe to these messages also allows you to quit early. So if the process dies in 2 seconds instead of 10 minutes, then you don't have to wait around. You know immediately that something wrong has happened. So that's what this is. And I'll be talking more about this in the monitors section, which you'll see in the section on supervisors. So yeah, that's about it. So those are the few things you should know. Of course, this could be refactored to, instead of running things like this, right? I could just delete all of this boilerplate, and instead of doing task.start, I could do task.await, and then task.async future. And why is it yelling at me? Because I don't have these functions anymore, these values anymore. And then let's simplify this. So this is kind of what we wanted, right? We wanted a scheme by which we could launch a concurrent process and then gather the future later. So recompile. And why is it still yelling at me? Yes, so the trick is to not confuse async and await. You want to async this and await that. And also to remember that task.await has a default timeout of 5 seconds, so we're going to just go ahead and do infinity. Is that right? Yep. And then we're going to recompile. And then run playground.heavylifting. We're going to wait for 5 seconds. We're going to heavy lifted foo and then done with foo. Okay, so this is a much cleaner interface and much cleaner code. So, the task module is really nice, and that allows you to avoid some of the boilerplate involved with running these sorts of things. Okay, so if you like this video and are excited about learning why the second reason why you want to use task instead of spawn, besides just the fact that task gives you async and await, subscribe to the channel, and I'll see you soon when I make my next video.